Hello everyone, I'm Shivani Dhok and today I will be presenting our work Parametric Channel Estimation for Near-Field RIS Configuration and Data Demodulation. This work was presented in IEEE Globecom 2025 conference which was held at Taipei, Taiwan. Here is the outline of my presentation. First, I'll discuss why near-field communication is relevant. Then I'll discuss why channel estimation for large RIS is critical, followed by the low overhead parametric estimation scheme that we propose, and then I'll discuss the results and key takeaways of our work. The upcoming wireless communication generations such as 6G and beyond are expected to deploy large antenna aperture arrays and operate at high carrier frequencies to serve data-hungry applications. The combination of large aperture arrays and high carrier frequencies leads to the user fall in the near field of the arrays. This is because the Fraunhofer distance that separates the near field and the far field regions increases quadratically with the antenna aperture and linearly with the carrier frequency. For example, when the carrier frequency is 30 GHz and the antenna aperture is 1 meter, then the Fraunhofer distance turns out to be 200 meters, which is significantly large, making the near field region relevant for communication. The near field region brings several fundamental changes in the channel definition. For example, the wavefronts which were well approximated as parallel in the far field region are now spherical in the near field region. To capture this spherical wavefront nature, the steering vector of the near field channel now depends not only on the angle of arrival or the directional cosine, but also on the distance between the transmitter and the receiver. For example, here we show the nth entry of the steering vector of a uniform linear array with directional cosine as omega and distance r. And if the user falls in the far field of the antenna array, then the steering vector is given by all the black font terms. Whereas when the user falls in the near field of the transmitter, an additional term pops up which is highlighted in the red font, which is inversely proportional to the distance between the transmitter and the receiver and quadratic function of the antenna index, inter-element spacing, and the directional cosine. This fundamental change in the channel definition requires us to revisit the conventional communication techniques which were specifically designed for far-field channel definition. Another technology that is coming up for the future wireless generations is reconfigurable intelligent surface or RIS. An RIS is a large surface of sub-wavelength sized elements and each of its element has a controllable reflection coefficient phi I with phase theta I. The channel between the transmitter ith element of the RIS is HI and the channel gain between the ith element of RIS and the receiver is GI. Then the cascaded channel gain between the transmitter ith RIS element and the receiver is given by the product HI into GI into the reflection coefficient e power j theta I. Since the signal transmitted by the transmitter is reflected from all the RS elements and then is received at the receiver, then the effective channel gain between the transmitter and the receiver is summation of the cascaded channel gains corresponding to every RIS element. Now this RIS element theta I can be tuned in such a way that we have constructive interference at the receiver. Or in other words, it can be optimally set such that it cancels the phase of the channel gains HI and GI, which can be achieved by setting it to be equal to minus of angle of HI and minus of angle of GI. When theta I is set in this fashion, then the effective channel gain is given by the expression here, which is summation of the products of the magnitudes of the channel gains between the transmitter and RIS elements and RIS element and receiver. When the RIS is optimally tuned, the SNR or the signal to noise ratio scales quadratically with the number of RIS elements. When the aperture of this RIS is large, then the user or the receiver falls in the near field of the RIS. And this is the primary focus of our work. as mentioned in the previous slide, the optimal RIS configuration is function of the channel gains HI and GI. Therefore, the accurate knowledge of these channel gains is critical. And the task that we need to do now is to estimate these n cascaded channel gains accurately, which can be done through different channel estimation protocols. One such example of the channel estimation protocol is given here in this figure, where we transmit n number of pilots to estimate the n cascaded channel gains. For example, in the first pilot transmission, let's say the first RIS element is turned on and the cascaded channel H1 into G1 is estimated, and at that time all the other RIS elements are turned off. Similarly, in the second time slot, the second RIS element is turned on and rest all of the elements are turned off. This allows us to estimate the cascaded channel gain H2 into G2, and this process is repeated for all the RIS elements, and hence we require total n number of pilots. And when this n is large, which is the case in the near field region, this channel estimation overhead is very large. But why do we care about this channel estimation overhead? Now, in a block fading model, the channel remains constant for a coherence interval. Therefore, we need to carry out the channel estimation as well as the data transmission in one coherence interval duration. Now, if we transmit more number of pilots, we get better estimation accuracy, but at the same time, the time available for the data transmission reduces, which lowers the achievable rate. Therefore, the question that now arises is how to reduce the channel estimation overhead and still have accurate estimates of these channels. And to answer this question, in this work, we propose a new parametric ML estimator. In a parametric estimator, instead of estimating the large dimensional channel gain vector, we estimate few parameters that completely define the channel vector. Now, since these parameters are fewer in number, in principle, the number of pilots required to estimate these parameters are fewer in number and much less than the number of RIS elements. This significantly reduces the pilot overhead. We also derive Kramer-Rao lower bound in estimating these parameters, and we extend it to derive the Kramer-Rao lower bound for the RIS-user channel gain. Now, these parametric estimates or the imperfect RIS-user channel gain estimate or noisy channel gain estimate is used to set the RIS configuration, which makes the RIS configuration imperfect or suboptimal. As a result of which, the AP-RIS-user effective channel gain becomes noisy. We also characterize this impact of noise on the RIS configuration and the effective channel gain. Now, this effective channel gain is required at the user to perform coherent data demodulation. So, we also derive an estimator which depends on the novel expressions for the statistics of the effective channel gain that enable coherent data demodulation at the user end. With this basic overview of our contributions, and now move on to go into details of our proposed work. And to do so, I'll first begin with discussing the proposed system model and the transmission protocol. So this is the system model that we consider. We have an access point or AP that wants to communicate data to a user with the help of an n element RIS. This RIS we consider as a uniform linear array. The channel gain between the AP and the RIS is the vector HBR. It is a deterministic line of sight channel and we assume it to be perfectly known. And the channel gain between the RIS and the user is a non-line of sight channel, a single cluster based channel model. And the channel gain is given by HRU, which is equal to G into B of omega and R. Now here, the three parameters that completely define this channel gain vector are G, omega and R, where G is the complex fading gain, omega is the directional cosine, and R is the distance between the RIS and the scatterer cluster center. Now, before transmission of the data from the AP to the user, the AP first needs to set the RIS configuration, for which it needs to know the channel gain HRU. Now, to enable its estimation, user sends M uplink pilots to the AP, using which the AP estimates the parameters G, omega, and R, and uh, which is given by G hat, omega hat, and R hat. And based on that, it then sets the estimate of HRU as HRU hat, which is equal to G hat, into the steering vector evaluated at omega hat and R hat. Once it gets the estimate of the RIS to user channel gain, it sets the RIS configuration as phi hat, and it also sends the or it also forwards the estimates omega hat and R hat to the user, which allows us to do some processing at the user, which I'll discuss in detail in the subsequent slides. Once the RIS configuration is set, the AP is now ready to send the data. However, the user still does not know the channel gain between the AP, RIS, and user, or the effective channel gain. Now, to enable its estimation at the user, now AP sends a downlink pilot to the user, and then using that received pilot, it estimates the effective channel gain. And once it knows the effective channel gain estimate, the downlink data transmission can be carried out. This is the 3 steps transmission protocol that we propose in this work. And now I'll discuss the first 2 steps, or the channel estimation steps of this protocol, in much greater detail in the coming slides. First, I begin with the RIS to user channel gain estimation, that is the step 1 of the transmission protocol, which allows us to estimate, which depends on the parametric maximum likelihood estimator approach. We focus on maximum likelihood estimation scheme because it does not require us to know the prior statistics of the large scale parameters omega r and even the small scale parameter g. So for this particular step, as mentioned previously in the previous slide, the user sends M uplink pilot. Let's say the mth pilot is given by ym, which is function of the RIS configuration phi m transpose, which is the RIS configuration set for the mth pilot transmission. Capital HBR, which is a diagonal matrix whose diagonal entries are the AP to RIS channel gain, and G into B omega R, which is basically the RIS to user channel gain. All the M pilot transmissions are stacked in a vector Y, which is of dimension M cross 1. And using this vector, the AP first estimates the parameter omega and R using this optimization problem. Now, this optimization problem is involved, and we can't get a closed form expression for omega hat and R hat out of this expression. Therefore, to solve this particular optimization problem, we consider a 2-step approach. The first step is a grid search step in which we obtain coarse estimates of omega and R, and then we refine these estimates using grid search approach to obtain omega hat and R hat. Since the grid used for this omega and R is coarse, our approach to obtain omega hat and R hat is much less complex compared to the grid search only approach. Now, once we have omega hat and R hat, then these values are plugged in to this expression here to obtain the estimate of G, that is G hat. And once G hat, omega hat, and R hat is obtained, the RIS to user channel gain estimate H hat RU is set as G hat equal to B of omega hat R hat. And using this RIS to user channel gain estimate, we set the RIS configuration as phi hat, which is whose nth entry is given here, which is equal to e power minus of angle of HBR's nth entry minus angle of HRU hat's nth entry. Now note that the RIS configuration is noisy because it depends on the estimate and not the actual channel gain. As a result of which, the effective channel gain is now given by the summation of HBR nth entry, HRU's nth entry, and the RIS configuration's nth entry. Now note that this HBR is perfectly known, so therefore this RIS configuration is able to cancel out the phase of the AP to RIS channel gain. However, for RIS to user channel gain, the RIS configuration depends on the estimate of HRU. Therefore, it cannot cancel the RIS to user channel gains phase, as a result of which the effective channel gain is no longer equal to the sum of products of the magnitudes of the P to RIS and RIS to user channel gains. So here we mention the effective channel gain, and next we characterize the estimation errors in these parameters with the help of the Kramer-Rao lower bound. Now this Kramer-Rao lower bound is a lower bound on error covariance of any unbiased estimator. The CRLB in estimating the parameters G, omega and R is a 3 cross 3 matrix which is inversely proportional to the pilot power and directly proportional to the noise variance, and it is also a function of the three parameters G, omega and R. Now this CRLB expression can be extended to obtain the CRLB in estimating the RIS to user channel gain, which is given by the Jacobian matrix HRU multiplied by the Kramer-Rao lower bound of the parameters into the Jacobian matrix Hermitian. Another use of this Kramer-Rao lower bound is the asymptotic efficiency of the ML estimates. It states that when we have large number of pilots, the estimation errors of these parameters are distributed as complex Gaussian random variable with mean 0 and covariance as CRLB. Now, in order to test for what value of m or for which value of m this asymptotic efficiency of ML estimates kick in, we use the Gaussian paper test experiment, in which we plot the Q inverse of 1 minus CDF of the error, which we refer to as CDF inverse of the error, as a function of error. The CDF inverse as a function of error is a linear curve, and as shown here in red. And when we plot the CDF inverse empirically, if the closer is the empirical curve to the linear curve, the better is the Gaussian approximation of that particular random variable. For example, here we consider the real part of the complex gain G's error, and the red term corresponds to the analytical expression, and the circles correspond to the empirical results for the Gaussian paper test. We see that the circle markers are very close to the linear red curve, even for the number of pilots equal to 35, and these results are for the number of RAS elements equal to 100. So even for m equal to 35, the asymptotic efficiency of the ML estimates kicks in, which makes this a very useful result in order to characterize the estimation error statistics. Once we have characterized these estimation errors, this brings us to the end of the first step of the transmission protocol. So now we know the estimate of the RIS to user channel gain. We have set the RIS configuration, and based on that we know how the effective channel gain looks. So the next step in our transmission protocol is to enable the user to estimate the effective channel gain after setting of the RIS configuration. For that, AP sends one pilot to the user, and the user receives the signal YC, which is function of the transmit power PC and effective channel gain and a noise AWGN. And then it constructs the LMMSE estimate of the effective channel gain, first assuming that the omega and R are known. However, the user will not be knowing omega and R because it was estimated at the AP site. Therefore, it will replace omega and R by omega hat and R hat, which it receives or which were forwarded by the AP to the user after their estimation. The LMMSE estimator of the effective channel gain when omega and R are known is function of the mean of the effective channel gain, variance sigma EQ square of the effective channel gain, transmit power and noise variance. Now, since the RIS configuration was noisy, the effective channel gain is affected by the errors in estimating the parameters G, omega and R, which in turn which in turn affect the mean and variance of the effective channel gain as well. Another thing to note here is that when we plug in this phi hat n expression in the effective channel gain expression, we see that the effective channel gain is a non-linear function of g, omega and r and their estimates. This makes the derivation of the mean and variance of the effective channel gain intractable. So now the question arises is that how to compute these mean mu eq and variance sigma eq square. To enable that, we present a linear approximation of the effective channel gain, which is a function of the magnitude of G, L1 norm of HBR nth entry's magnitude, and error terms. The first term in this expression here corresponds to the effective channel gain when the RIS configuration is set based on the true value of HRU. And the second term, which we highlight in red, is a function of EL, where EL is the vector of errors corresponding vector of errors in estimating the RS to user channel gain parameters. Therefore, this captures the impact of errors in estimating G, omega, and R. Using this linear approximation, the mean of the effective channel gain is obtained as a function of the variance of complex gain G, number of RIS elements, and L1 norm of AP2 RIS channel gain. And the variance is obtained as the summation of two terms, where the first term is the variance of the effective channel gain when the RIS is set based on HRU, and the second term captures the impact of errors in estimating G, omega and R, which depends on the the uplink pilot power, noise variance at the AP, number of RIS elements, AP to RIS channel gain, and delta NM, a constant which depends on the Kramer-Rao lower bound. Once we know these expressions of mean and variance, we can plug them in the effective channel gain estimator equation here. Note that these expressions depend on Kramer-Rao lower bound delta Nm, and delta Nm depends on omega and R. And therefore, this this sigma eq square is a function of omega and R. And in this particular expression, omega and R are replaced by the estimates omega hat and R hat. This brings us to the end of the estimation of effective channel gain. Now the user knows the effective channel gain for coherent data demodulation. So now the AP can go ahead for data transmission. Now I'll move ahead to discuss the impact of various system parameters on the mean square error in estimating the RIS to user channel gain as well as the effective channel gain, and also characterize the impact on the coherent data demodulation. So first I discuss the impact of various system parameters such as number of pilots, RIS to scatterer cluster distance, and directional cosine on the mean square error or normalized mean square error in estimating the RIS to user channel gain HR. The first figure here shows the normalized mean square error or NMSE as a function of number of pilots. And all of these three figures show the results corresponding to the proposed parametric near field ML, which is the black curve. We also compare it with the parametric far field ML, which is shown here in the purple curve, and we benchmark it with the normalized CRLB, which we had derived earlier. The first figure here plots the NMSE in estimating HRU as a function of number of pilots. We see that all the three curves initially decrease and then saturate, and the saturation of the NMSE occurs at m equal to 35, which is much less than the number of RIS elements. So sending more pilots or pilots more than 35 is of no use, because the NMSE has already saturated and it does not give any gain in the normalized MSE or in the MSE. Another interesting thing to note here is that the number of parameters that we were estimating are 3, which is G, omega and R. But when we send only 3 pilots, the NMSE of the proposed approach is very high. It is even more than 1. So this implies that the parametric estimator is very sensitive to noise when we send very less number or small number of pilots. The second figure here plots NMSE in estimating HRU as a function of the RIS to scatterer cluster distance. We see that as the distance increases, the NMSEs of far field and proposed approach decrease and then saturate. We also see that the parametric far field ML approaches NMSE slowly approaches the NMSE of the proposed approach. However, there is significant gap between the NMSEs even in the far field region that is greater than 50 meters or the Fraunhofer distance. The third figure here plots the normalized MSE as a function of directional cosine. We see that the proposed approach NMSE is insensitive to the value of omega. However, for the far field scheme, the proposed approach for the far field scheme, the MSE initially increases and then decreases. So basically, it is a concave function of the directional cosine. Next, we perform performance benchmarking and also characterize the NMSE in estimating the effective channel gain and the and its impact on coherent data demodulation. We consider different schemes for comparison. First of all, our proposed approach is a near field parametric ML scheme and it uses omega hat and r hat. Therefore, we name it as NFPML, omega hat and r hat. We compare it with the scheme when the when the effective channel gain is estimated assuming the true values of omega and r. That particular scheme is referred to as NFPML omega r. We see that the NMSEs of all the NMSEs and SEPs of all the schemes decrease and then saturate. Another interesting insight is the NMSE of our approach, which is in this blue triangle, overlaps or it has negligible difference compared to the NMSE of the NFPML omega r, which assumes the true knowledge of omega and r. We also compare our scheme with different schemes which include far field parametric ML, which only estimates the directional cosine and not the distance, and it also estimates the complex gain. Then we compare it with non-parametric ML scheme, which estimates or which obtains the ML estimate of the entire channel gain vector HRU. Then we also consider OMP, that is orthogonal matching pursuit scheme, which is a compressed sensing based scheme. And we also consider a codebook based or near field codebook based scheme. We see that our proposed approach attains lower MSE and SCP compared to all the benchmark schemes. We also compare our scheme with a perfect CSI scheme. By perfect CSI, we mean that the AP knows HRU and it sets the RIS configuration assuming HRU is known. However, the user still doesn't know the RIS to user the user still doesn't know the AP RIS to user effective channel gain. Therefore, it still estimates it, because of which the estimation error or the normalized MSE for perfect CSI is also non-zero. However, for large SNRs, the NMSE of our scheme attains the NMSE of the perfect CSI scheme. Similarly, the SCP of our scheme attains the SCP of the perfect CSI scheme for large SNRs. With this, we come to the end of the presentation. We have proposed a low overhead parametric ML estimator scheme for an RIS aided near field communication system. We showed that the number of pilots required by our scheme are much less than the number of RIS elements. However, they are much more than the number of near field channel parameters to be estimated, which implies that the parametric ML estimator scheme is very sensitive to the noise when the number of pilot transmissions are fewer. We also presented an effective channel gain estimator and studied its impact on coherent data demodulation. We derived novel expressions for mean and variance of the AP RIS-user effective channel gain, and this was based on a novel and tractable approximation of the effective channel gain. And we showed that our approach results in a lower MSE and lower symbol error probability, that is SEP, compared to several benchmarking schemes which span over far field schemes, non-parametric ML schemes, compressed sensing based schemes, and codebook based schemes. For further reading, we also have a journal version of this work, which has been recently accepted in IEEE Transactions on Communication. In that extension, we present achievable rate characterization of the proposed scheme in the presence of noisy channel estimations. We study the pilot and data transmission trade-off corresponding to the power allocation as well as the time allocation. And we also present extensions and generalizations of our scheme to multi-antenna AP, multi-cluster RIS to user channel gain, uniform planar array RIS, and multi-user systems. That's all from my side. Thank you for your attention.